Okay, now we continue with section 2.1. As I said, the main goal now is to go over some examples. So we'll go over the concept of secant line to a graph, and how we use this to obtain the slope of the tangent line. But in order to do so, let's go over a small review of linear functions. In reality, they are really called affine linear functions. These are functions of the form f of x is equal mx plus n, or ax plus b, where m is the slope, and they look like this. And the slope, as you see here, is a constant specific to the function f of x. So it's always the same at every point, and this quantity m corresponds to the quotient delta f divided by delta x, which is well defined. So if you pick any given delta x and we look at the change in height of f, this quotient here, delta f over delta x, happens to be a constant, and that's what defines the slope of the linear function. And here's just the value of f at 0, so this height over here. Later on we'll use other expressions for a linear function. Remember there are different formulas that we used in previous courses, but for the purpose of introducing instantaneous velocity, this is the good way to go. Okay, so now we know that the slope of a linear function is well defined. We can compute slopes of secant lines. Okay, so we now need to look at a somewhat larger graph to illustrate this concept. So let's consider a nonlinear function now, f, and let's consider some point here, a. And this height here corresponds to the value of f of a. And let's suppose that we're just moving away from a and we're adding a certain number h to a. So this thing here is h. If we add that length to a, we're sitting at a point a plus h. This is the point x equals a plus h. And at this point, we get another value of f of a plus h, and we can consider the line that passes through these 2 points. And this is a linear function. If you remember from previous courses, any 2 points in the plane determine one line. In this case, this line is L, which is the secant line. And correspondingly, it will have a slope. Remember that the slope corresponds to this, which is delta x. I mean the quotient between delta f and delta x. So this is delta f, and this is delta x. What is delta f? So the slope of the secant line L of x is given by delta f divided by delta x, which in this case is equal to f at the point a plus h minus the value of f at a. So it is equal to f of a plus h minus f of a, and delta x is just h. It's given by h because it's what we added to a to get the new point a plus h. Right, so this is the slope of the secant line. Now, if we start getting closer to the point A, so if we take new values of h, let's draw the graph down here, and let me be a little bit more careful when I'm doing things. So now we consider different values of h. So here we obtain one secant line, so we give ourselves a number h, we added it to a, and we obtain a secant line passing through 2 points on the graph, one corresponding to the point a, comma f of a, and another one corresponding to a plus h, comma f of a plus h. Now we'll consider more points, and we'll actually let h become smaller and smaller. And this is the graph. Of f, and these are the 2 initial points, a and a plus h. And now we have the points f of a and the point f of a plus h. This is just a starting point from the previous drawing. Just put everything in the same graph. We'll use a color this time. So we have one secant line corresponding to the blue line, which will have its own slope. And now we can also consider a smaller value of h. This will be a plus some other number h1. obtain a new secant line with its corresponding slope. Now if we take a different number h2, smaller than h1 and h, so I'm just completing the graph here. Then we have another secant line. And with its corresponding slope. So each of these lines will have each one of these lines have a corresponding slope. F of a plus h minus f of a divided by h. When we consider a smaller value h1, we get f of a plus h1 minus f of a divided by h1, f of a plus h2 minus f of a, all of that divided by h2. And the idea here is that if we continue with smaller values h sub n or h sub k, for k large number and for which h of k is very small, is getting smaller as k gets larger. So in here, if we consider say a plus h3, we can consider more and more numbers. This could correspond to a plus h, say 1000, say. So we're approaching 0. Then delta f over delta t changes naturally in most cases, unless the function was linear to begin with, but it may approach so we're using delta x here, right? We may approach value L, which will be the limit we are considering a sequence of numbers corresponding to slopes of secant lines, and if these values start approaching a certain number L, we'll call that of course the limit, and that will correspond to the instantaneous velocity. In other words, the instantaneous velocity is equal to the limit delta x goes to 0 of the average velocity or instantaneous velocity the limit delta x approaches 0 of delta f over delta x. Here remember that, you have to be careful when trying to evaluate when delta x is equal to 0, because delta x is getting closer to 0, delta f is getting closer to 0 as well. So the values of f at the endpoints are getting closer and closer to. But we have one final expression for this, which is the one we use when we define the derivative. This is in parentheses. So limit of f of a plus h minus f of a, all of that divided by h. This expression here will be used later. And again, this should not be surprising, because the notion of derivative simply corresponds geometrically to the slope of the tangent line. And you see now that the concept of limit appears everywhere, and this is going to be the case for the rest of the course. Maybe it will be hidden after we learn how to compute limits without actually having to deal with these very small quantities, because we'll learn some rules that will allow us to compute these things very naturally. But for now, at the very beginning, we just have to understand that this is something is behind everything we'll do. And in fact, for those of you who will take Calc2, the integrals are also defined as limits, so they appear everywhere in calculus. You started from algebraic things in previous courses, and now once we introduce the notion of limit, we can start talking about slopes of secant lines and area under a curve and instantaneous velocity and things like that. Area under the curve, of course, is something for Calc2, but for now this is still early stage to starting talking about these things, but it plays a big role in what we're going to be doing in the next few weeks. Okay, so we'll be computing limits by hand, and we'll be talking about derivatives and such. So we need to understand how to proceed to obtain these numbers L, that these expressions approach as a certain number goes to C, or when delta x approaches 0. Okay, so now we'll go over some examples in the next video, and then we'll begin with section 2.2, which is the one that carries the most weight for this week. It's the most important one, and the one where we actually learn how to compute limits.